Yo, what's up, everybody? Welcome back. Today, I want to fix the fact that when I play Arc Raiders on Linux, also on Windows probably, but on Linux specifically, I want to fix the fact that it's too damned dark, man. So I've been playing a lot of Arc Raiders, so much that I've been kind of neglecting stream, to be honest. But this is what the game looks like sometimes. Look at this shit. Look at this shit. You can't see anything. You can't see anything. And it turns out that if let's find another, look at this. You can't see anything down this hallway. But it turns out that if I change my monitor settings, you can see, right? So it's kind of bullshit, but the game is balancing itself around visibility, but you can do things to improve your visibility, things that are not even detectable by the game, right? I just go into my monitor settings and I increase gamma, and I can see down that hallway. And so it's this is something that I don't want to have to be doing. I don't want to have to change my monitor settings and make every video that I watch look like shit just so that sometimes I'll play the game. And I also don't want to have to remember to toggle my monitor settings every time I change maps or open the game or whatever, right? So on Windows, what people do is they open up their NVIDIA settings and they apply all these filters, right? They change the gamma, they increase digital vibrance, they increase change the brightness and contrast. They might even apply some filters to do some digital sharpening. There are all these things that people do to make the game more visible, which I kind of think is cheating, but not in a way that is preventable. And so it's one of those things where it's a race to the bottom where everyone's doing it. And if I die to someone who can see me in the dark and I can't see them, it's just fucking frustrating, right? So I play on Linux, and I don't have these same settings panels. I also have an AMD card. And as far as I could tell from a quick Google, there's not a similar utility to the NVIDIA settings that will give me what I want. And so I figure let's just make something where I can limit myself to what I think is reasonable. I think emulating what my monitor is doing when I press the buttons on it in software is relatively reasonable. So changing the gamma curve, I think, is relatively reasonable. Maybe playing with brightness and contrast are both things that I could do on my monitor as well. So maybe I implement those. But the goal is just to make the visibility somewhat sane. And so to do that, first we might want to explain a little bit of the graphics stack that is happening here. So I am running this game in a Wayland compositor called KWin, right? KDE's window manager. This guy is kind of the guy who owns drawing to the screen, right? So everything on this screen goes through KWin. He talks directly to hand wavy the AMD GPU driver. Well, directly is maybe a little bit of a thing. He kind of talks to the AMD GPU driver through a kernel mode setting, which is a kind of generic kernel interface for things like setting up monitors and buffers and stuff like that. And then there's also kind of Mesa, who kind of owns the Vulkan / OpenGL / shader compilation pipelines and all of that stuff. He's kind of talking to them through these guys. But I think that there might be some cases where you can talk directly to him. I'm not really sure. My game is kind of running up here, right? Game. And he talks to KWin, right? So anything that I want to happen here anything that I want to change the visibility in the game has to happen here or below, right? This game is running in Steam. It's a Windows game, so he's running through Wine/Proton, right? And there's this thing called, I believe it's VKD3D, I think is what it's called, which is basically a translation layer between shaders written for Windows graphic system that converts that into Vulkan shaders. And so you can kind of hook something here with these things called Vulkan layers or something. And I believe, I didn't look too closely here, but I believe that these allow you to apply arbitrary shaders to the game, which is kind of hype. You can kind of do all sorts of crazy shit with that. However, when I was doing some research here, I stumbled across Steam's compositor called GameScope. GameScope is this it's basically like what they use on the Steam Deck, right? So like they want to show Steam in something and they need like a like basic window manager to do that. And this is how they do all of those things, like apply sharpening in every game, all of like those like weird features on the Steam Deck where you can like upscale and like limit resolution, all that. It's kind of handled by GameScope. This also does stuff like some color temperature stuff, like it lets you do like night mode, all of that stuff. But in here, they kind of talk about the idea that using shaders for doing simple transformations, which can be achieved with lookup tables or color transform matrices, I believe is what CTM stands for, which are possible to do on the display core on AMD GPU at scan-out time. It's like, don't do it with a shader if you can get away with it, because it's like way less efficient, right? And I believe them. So I was fiddling around with settings here, and I found in the display section here, there's this color profile thing. And in here you can apply an ICC profile. So you like start looking into like what an ICC profile is. Isn't finishing your own compositor and making per app brightness profiles the feature the way to go? Not if I want this to work in like the next week. Right? We'll be honest, I'm not gonna finish my compositor into a place where I can use it to play games probably for like months, maybe month, but like it's gonna be a while. So this is easier. So you can inject color profiles in here, and these ICC profiles, what they're used for is, I believe typically they are used by like artists. So like you basically like buy this like fancy camera and you like staple it to your screen or something, and like on the monitor you start like turning on colors, and that thing will be like, oh, the red isn't the right red, so like here you need to adjust like your red by this much and your green by this much, your blue by this much. Like the response curve of your monitor isn't quite right. These ICC profiles are also used for capture as well as for output for printers, right? So there's they I believe they said they have display input and output devices, right? So like if I capture something on my camera, I might have a calibrated profile for the images that I take with this particular camera that adjust the curves. Then I will have another profile for my monitor to display those correctly, and I'll have another monitor for my printer to make sure that they come out correctly on the other side, right? But basically, like the idea of these things is fuck up your colors, bro. And when we're looking at the implementation of these things in Kwin, it looks like they're using what is suggested by this like GameScope thing, where they kind of hook into the kernel mode setting features, like the generic low-level monitor features of Linux, like they like set up and adjust the CRTC pipelines. And in there, we looked at like the AMD GPU code, and it looks like we're hitting some like optimized path for that. So it feels like, given that this thing exists and people are using it, and it looks like it's taking an efficient path, I think that it would be interesting to try to apply these profiles and see what happens. I remember listening to a conference video where a Kwin maintainer said they ignore most of the SC profile transformation and prefer accuracy mode. Beware. Or prefer efficiency mode. Beware. Yeah, okay, makes sense. Thanks for the heads up. So yeah, I think step one today, if we can figure out what the fuck an ICC profile is, like at a low level, I think we'll be in a pretty good spot. So I've downloaded a couple. I googled like gamma ICC just to like see if there are some that exist. And I want to see what this thing might look like, right? So we have some proof here that if I open this thing, I in MPV ask it to open with a profile, and then I also compare that to in MPV without the profile. Hold on. We will see a difference visually. However, here, where were we? We're like here, like around here, right? You can tell that we've like definitely fucked up something, right? Like it just looks, it looks messed up in one of these and not in the other. Wow, this is like, that's surely a bug, right? That resizing MPV is this slow. So anyways, there's something here. Let's see if we can like make this do something that we want it to do. So let's just look at this thing. If we just do a little maybe copy downloads sRGB, 0.55 gamma ICC to like here, and we like hex dump this thing. We can see some pretty good like info about what this thing is just by looking at the hex dump, right? So typically, I mean, we see like some headers or something, right? Here it looks a lot like we're seeing some descriptions of sections of the binary, right? Like this is like a pretty common thing where you might have a binary format will have a list of things at the front that are like, here are the things in our binary, and you can look at them at these offsets, right? So we saw that kind of in our text rendering stuff when we did TTF parsing, as well as in our PNG decoding. I think we saw the same thing. Where there's kind of like a list of stuff. And the reason I'm saying this is you see a bunch of like very short but human readable sections, right? So like 4 bytes then description. You see like, oh, this is something about, you know, XYZ. You see something about like XYZ, G, B, right? Something. So red section, green section, blue section, maybe. Maybe the green section is like twice as long or something, and so requires like 2 sections, maybe something like that. You have maybe like a different color space or like a transform or something, RGB here. And then down below, we saw a bunch of human readable floating point numbers, right? So we can maybe guess that there's some sort of like lookup table here, right? Like at maybe, I don't know. We don't know yet, right? But there's something here. I think that it is probably reasonable to look up the ICC file format spec. I think I found this somewhere at some point. Spec, maybe? Maybe this is where I found this thing? Defines a file format. This is what I want. Current spec. Slap that shit. All right. And I think maybe it's time to just try to start writing a program that can start interpreting this thing, and we'll kind of see if what comes out of it. Let's see. Okay. So it looks like basic, they've got some number types. They got floats, positions, a bunch of like signed and unsigned fixed numbers. Cool. We'll come back to this stuff. This stuff probably doesn't matter right now, right? This probably only matters in the context of parsing something else. So I want to kind of see like the overall like format of the file is kind of the first thing that I want to look for. Tag table. Okay, here we go. This looks kind of reasonable. Profile requirements here on page 18 is probably where we want to start. 17, 18? 17.3. Very cool. So it's probably like here. Okay. An ICC profile shall include the following elements in the order shown as a single file. Perfect. A 128-byte profile header. This is going to end up with you blowing up a bunch of legendary monitor calling now. Surely the monitor won't let that happen. Surely it's not even possible, right? Because the ICC profile, as far as I understand, is being applied on the GPU. So I believe the GPU only has the ability to output like numbers in a range that the monitor knows how to process. I don't think it's possible for him to like overclock the fucking pixels, right? Like, I don't think so. Okay. Profile header as defined in 7.2. I think we just skip everything else and just go to 7.2, right? That's probably because that's the first thing. All right, here we go, baby. This is the fucking thing. This is the fucking thing, man. Okay, so we start. Okay. So maybe what we do is we just copy paste this table and figure it out from there. If it will let me. Here we go. Copy. And I guess let's do a little web function main. And let's open a file. fs current working directory, open file of what is in here. This guy. And LLM make this a struct. No. Macro make this a struct. Okay. So let's do this. Delete a few words. Go go, 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 delete, go, 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 delete, go, 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 go. Okay. Then we see, I guess for now, let's just double check that we have 4, 4, 4, 4, 4, 4, 1, 2, 3, 4, 5, 6, 12, 12, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 8, 4, 12, 4, 16, 20. Okay, cool. So each of these guys is going to be times 4. So in terms of like bit size, how do we want to do this? This is a U32, right? Boom, 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 boom. Every 4 U32. This is a U64, U32, U32. This is 16. So anything above 8, I think we bring into its own struct probably. So we probably have date time number for now is we'll just stub it out as 3 U32s or something. Right, so this should give us oh, oops, it's like this. Reserved U32. I forgot which language we're writing. It's a hard life here. Okay, so that's this guy. Then 12 is the XYZ number. I'm going to assume, based off what we saw in the hex dump, that this is 3 floating points, but we'll come back to this. Right? That's kind of here. Then we have profile ID. So profile ID, I'm just going to have like this because I don't really know. So I think I'm going to like just kind of throw 16 U8s at that thing. And then 28 bytes reserved. Sure. Okay. So now we should be able to start doing things like this is header is a struct, packed struct. Because we want it to kind of follow some rules here, making crabs thing for the prime. So profile size here, boom. We've got preferred CMM here, boom. Version, boom. Device class like this. Color with a U. This probably needs to get a more advanced type, but we'll live. Date is like this. ASCP like this. Primary sig, I guess, is a good name for that. Profile flags like this. Manufacturer. I bet you this is supposed to be a 4-byte thing, not like a U32 packed. Like it's not supposed to be like a number, probably. Model. Device attributes. Sure. Intent. Rendering in intent like this. NCIE XYZ. I guess we'll call this for now. Creator. Profile ID. Boom. Reserved. And maybe we just do a 28 U8 inline here. Okay. This maybe is something. So can we do something like F reader probably, and let's just do unbuffered for now. Oh, fine. Var reader buff is a fucking this guy. We use this in our reader. And we do like this, and then we try to read this thing. So it should be like interface take struct of header. And what is the endianness of this stuff? That's the first thing that we have to answer. Creator with a U to be consistent with the color. Actually, I don't think that's how it works in fucking non-America English. I don't know. Y'all dropped a lot of U's, but that doesn't mean everywhere where there's an O that we add one. Okay. Where was this UN32 number? I think I want to like open this in a separate tab so that we can scroll around. UN32 number. Okay. Unsigned 4-byte 32-bit integer. But like, what is our endianness? What is our endianness? Big. Okay. Let's see what happens. Let's see if this header seems sane in any way, shape, or form. Date time number. Oh, does this guy also need to be packed for it to like kind of propagate correctly? Why? Packed structs cannot contain fields of type 16U8. Okay. Why? Do I want to do extern struct then? To force like C and C formatting instead? Yeah, okay. Cool. I wonder, is there like a better ICC profile for us to use here? No, that's not what I'm looking for. Maybe this guy? This feels more like what I want. What do we call this? It was capital S sample. So we have profiles here, sample profile. Let's try this. I just want to see if like the data in there is like a little bit more sane, you know what I mean? Because this guy like just generated some for gamma. I want something that's like meant for testing. Okay. Okay, so he does have like a creator and profile ID now, which is huge. Looks like our floating point parsing is obviously wrong. Profile size maybe looks right. Do you or what do I want? I want like character count on this sample profile. So 8208. Good news. At the very least, the first field is correct. At the very least. Preferred CMM. Okay, so let's just start reading through this thing and trying to parse out the things that we care about. I guess. Maybe we care about everything. I don't know yet. 7.2.3. Preferred CMM type field. Bytes 4 to 7. This field may be used to identify the preferred CMM to be used. I don't know what a CMM is yet. If used, it shall match a CMM type signature registered to the ICC tag registry. C clause 5. If no preferred CMM is identified, the field should be set to 0. All CMMs should be registered with the ICC. Okay. Why is this such a big fucking number? Right? That seems kind of fucking wrong. Can we hexdump this thing and compare? Sample ICC profiles, sample profile. Maybe less. So we are expecting. It's a string. It's a string. I see. So let's do this. Maybe we want to do like. I would like this to be like formatted a little nicer. So maybe here we kind of do this. Or we could have this guy be like a packed string or something. Maybe of like this. And he returns like a struct of where he has an inner value of size u8s, right? And then he can say in here, let's render this thing as a string. You know? That seems kind of nice. So this probably takes himself as well. And here he's like W write string. Do we have that? Byte? Print splat bytes. Print write all. That's what I'm just looking for. I think this is it. So now this guy can be packed string of 4. And that should extra instruct cannot contain this type. What if I do this? Nice, except he didn't fucking print this thing nicely. What's the point in having a format on there if it doesn't print nicely? I guess that means that we do have to do it here. That's okay. That's okay. So what does like the default thing do here? He prints out the struct. I guess we go like for stud meta fields of header, probably inline field here. We say something like w print something like this equals, they do like a dot in front, equals this. Oh, what a pain in the ass, dude. So then you have to switch on the type, right? Oh, I guess you can just call W format on the field, maybe? I don't know. Maybe even then you can do this? I don't really know if you can do F for everything. Probably not, right? Is there no format on here? What the fuck? How does this guy work? Maybe print value? Value any type? Format like this? Oh my god. So I have to get the fucking format right? No way. No way. No way. Is there no way to just be like fucking huck a thing over there? I guess we can just throw an any on there, but then if we have a format method, we should call F, or we can call any. Maybe that's the trick here. It's like a switch, like format string is like if has decal oh my god, dude. Field type of format, then it's for like this, else any. Is this really the way? This feels so fucking stupid. But maybe this is how you do it. I don't know, man. I'm just trying to fucking print a thing. I'm just trying to print a thing. Then this probably gets like a comma and a space or something. Found U32. So true. Oh my god. Switch on. This is so stupid. I'm sure I'm missing something that's like nicer here. But whatever. Okay, if we're struct, then we do this. Otherwise, it's just any. Let's try that. Type info, I guess. Jesus Christ. Array, literal. Oh, that's here. Okay, we fucking got there. Try derive debug. Yeah, sorry, my bad. There we go. Okay, so we probably should put the apple in string there. Right? This should probably be W put right byte a quote on both sides of this thing, so it's clear that's a string. What the fuck is this pissed about? Expected type U8 found. Oh. Fine. Fine. There we go. Cool. Cool. So now we finally, all of that to get this part parsed correctly. Let's fucking go. Let's fucking go. Okay, profile version. Let's look at that. Profile version. We're expecting this to be a 4-byte number. 420, blaze it. Nice. Or this is probably big endian. Yeah, so 4200. So maybe we want to show that as hex? That's a really high number. Like a really high number. Are we sure that we got that right? Bytes 8 to 11. 8 to 11, yeah. I mean, that's just a... Maybe it's like 4.2.0.0 or something. The first byte shall identify a major version, and byte 9 shall... So yeah, so it's major, minor, 10 or 11 are set to 0. Oh, I see. It's 4.2.0. That's kind of what this is supposed to be. So this is supposed to be like a const profile version. Let me think. Is it easier to not parse this way? I think it is, right? I think it is. So I think trying to just cast this thing like this is going to get more complicated the farther we go, right? Because we're kind of limiting ourselves to things that are supported by extra instruct. I think I'd rather actually have this have like a parse function from a reader. And I'd rather go by hand, to be honest. I'm pretty sure I would rather do it that way. So this returns a header. And what we're going to do is we're going to go... each of these guys... I think we can just return like this. And then we should be able to start like by throwing a dot in front of everything here. Probably replacing the colon with an equals. And then these, we just need to replace this with like a R read int, R take int. Here we go. And then this should be a macro, I guess. R take int big. And then this should be tried. Okay. And then I fucked this up a little bit because there were too many go downs at the end. Did not fix it, but like whatever. Yeah, wait, what the fuck? There we go. No, it is jumping down every time. What the fuck? I don't know why that's not fixing it, but whatever. And it looks, I'm a little worried that, that we have a problem here, but whatever. Like, why is this not syntax highlighting correctly anymore? I'm confused. Am I missing brackets somewhere? Let's just try to compile and see where it gets mad. Sure. So this should be, header parse now. Header is try here. Expected pack stream from type. Oh, I see. I think it's like this, right? Take 4 bytes or something. No function take bytes. What is it then? Oh, there we go. We're back. We're so back. Okay. Is it bytes? Read byte? Take bytes. Read all, maybe? Yeah, I guess it's kind of more like CMM is 4U8. I guess I kind of want it like this, right? So we start with this is undefined. Oh, but then it has to be in order. Fuck. Fuck, that's annoying. That's annoying. Because is there really no take bytes? Like, it feels like there should be. Take all? Take array. Maybe is what they want. Nice. And then this copies, right? Yeah, nice. Returns the next end bytes of stream, filling the buffer as necessary and advancing the seek position. Asserts that the reader, if there's no fewer than this, but also take. Oh, it's just take. I see. And then this guy has to be, I guess like this is probably how we're supposed to do it. Maybe this stuff for now can be like this, and then we can call take struct on these. I don't know. While we fix them up. Yeah, there we go. Sure. Sure. Close. We need to, the dereference has to be after a try. So true. So true. Big. Big, 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 big. We are big, big, big boys. Another one down below, like this. Not a struct on profile ID. Oh, interesting. What is profile ID? Okay. There we go. Okay. Cool. Hi, is this Rust? It is Zig. So now we can get a little bit more advanced here, right? So our profile version here is supposed to have major, minor, and major, minor, patch. And this guy can now be packed struct, which is fine. And then this guy can be take struct here. And now, because before extra structs, I think couldn't have U4s in them, but packed structs can. And this just will behave a little bit more sanely. Okay. Profile version. What we got here? Expected type U32. True, because this thing has to be a packed profile version here. What about the 2 reserved bytes? So true. So true. Which it won't like. So let's do this instead. So this is going to be a self profile version. Or no, he's going to be like reader. Stood IO reader. He's going to return a profile version. And this guy's going to be like return. Major is our take byte. Minor is, I guess we have like this. Major is like this. Minor patch is our take byte again. And then we have our toss 2 here. Get rid of the next 2 bytes. And then here we can go major is major. Minor is minor patch shifted up by 4. Truncated. Boom, boom. And patch is truncate just the way it is, right? Does truncate have well-defined, like, pick the upper or lower bits? Always truncates the significant bits, whether or not... Okay, perfect. Okay. So the ICC's API can handle versioning itself, or you need to create a backup auto before running the file. I don't know. I have no idea. You know as much as I do right now. We have not tried very hard to understand shit. Parse from reader. Expected area unit type found void. Skips the next end byte from the stream, advancing the seek position. See, also discard. Maybe that is what I want. Limit. Okay, yeah, maybe that's what I want. Discard. Maybe like this is what they're asking for. This guy has to be tried, so true. Okay. 420. So that lines up with what we saw in the hexdump, which is pretty hype. And next up, we got device class. This field shall contain one of the profile class signatures shown in table 18. This is table 18. There are 3 basic classes of device profiles, which are input, display. Okay, so the first thing we need to do is render this as a packed string. Right, so this will at least tell us if it looks sane. So how did we do this? It was like this. Device class. So we have monitor, MNTR, monitor, display device profile. Let's fucking go. Okay. I want this, by the way, this packed string thing to have a parse function that takes in a reader and returns a this. and maybe errors out, and then he can kind of do this stuff here, where he returns this guy. Returns inner our take array size though instead of 4. And now these guys get a little nicer. We have packed string for parse r, and it's really kind of, the compiler will auto resolve, so you don't even really need to fucking throw the type in front. You can just go like try parse r, boom, easy. And so color space, I assume, is the same shit, right? Yep, same shit, right? So we have 4-byte strings. Color space, packed string 4, boom. So RGB, nice. Nice, we're getting somewhere. PCS field shall be either PCS XYZ or PCS lab. The signature is defined in table 19. So this is the same thing. Same thing. Which we need to say try parse r. Nice. So PCS, whatever that means, is in XYZ space. And then color space is RGB. Exciting stuff. Date, I think I'm likely to just skip. Encode as a datetime number. I think I don't give a fuck about this, so I'm just not gonna bother. Profile, why Linux and not Windows? Because my computer runs on Linux. What do you mean? Are you asking why I use Linux in general? Because I like it more. Every time I boot Windows, I'm like, what the fuck is this piece of shit? Like, is about the extent of my thoughts on it at this point. Like, you fucking, like, try to open a program, you just get, like, shoved, like, 5 ads in your fucking face in your start bar. You're like, my friend was sending me that his work computer just forces the fucking Copilot thing into his quick launch. If he, like, removes it, it just comes back the next day. He's like, that's fucking crazy. They just have, like, ads everywhere. And, like, just, like, I don't know, you hit the start bar and you see like a picture of the president of the US. I'm like, I don't fucking live in the US. I don't fucking give a shit. Get the news out of my start bar. Like, what the fuck is going on? Like, says guy not running uBlock. At least on the internet, it's kind of like more opt-in. But then also, like, Linux gives me a lot of other stuff that Windows doesn't. You know, it's just, I'm more comfortable here. I feel like development experience is nicer. I feel like I can do what I want more. I feel like everything's more customizable. It's just a win all around. Poor RS84. Yeah, sorry, I wasn't yelling at you. I'm just yelling at me. Primary platform field, again, is a string. So that's this. I'm assuming, actually, that a lot of these, 4-byte things are going to be U32s. Why Linux gets raged at. I wasn't raging at him, I'm raging at me. What the fuck is an ASCII? Wait, did I miss that? Date? Oh yeah, I just did miss ASCP. What the fuck is that? ASCP. Do we need that? Who knows? Oh, this is a profile signature. I see. So this is also going to be a parse r. This is, we're starting to see a trend here, I think. ASCP, Apple, cool. Do I care about, like, any of this stuff? Probably not, right? Probably the thing that we're going to start looking at next is probably these, like, NCIE, XYZ stuff, right? That's probably the stuff that matters. Yeah, like, device attributes. I don't really care about this right now. Device model or manufacturer, I really don't care about that. Rendering intent, this might matter. When this profile is combined with the no profile in a sequence of more than 2 profiles, it applies the combination of this profile and the next profile in the sequence and not to the entire sequence. Therefore, this flag may not have any meaning until the profile is used in some context. Interesting. Least 16 bits shall be used to encode the rendering intent. The most significant 16 bits shall be set to 0. Defined rendering intents are perceptual, meter relative, color metric, saturation, IC absolute color metric. Interesting. So we'll have to come back to this, but I think that this is going to be relevant and we should parse it. So this is rendering intent is going to be a rendering intent rendering intent, so enum, who has perceptual media relative saturation and ICC absolute. Okay. And then this guy needs a fucking parse function. And this is this a bit field? No, it's crazy. This is the bottom 4 bits, not the bottom 16, but whatever. So this is our take int U32 big Indian. And this is a stud meta enum from int to enum. So this can fail. And this is going to say, we are trying to get a rendering intent from this value, or else return error invalid intent. And then this guy becomes a parse function here. What's he fucking miss about? Expected optional type? Wait, where? On 60. What did I fuck up? Oh, is this available? Oh, it is. All right. Nice. All right. So we have a rendering intent on this thing of perceptual. And then can we also compare with the gamma thing that we have? Which was sRGB. Is this also perceptual? Media relative. That's interesting. We'll have to keep that in mind, that some things may show up as like a visible thing when we apply them to our videos, and some things may not, and it depends on the rendering intent maybe. Right? PCS illuminant field shall contain the NCIE XYZ values of the illuminant of the PCS encoded as an XYZ number. Who the fuck knows what that means? The value when rounded to 4 decimals should be this. Okay. Weird. So is this, like, how are these things encoded? XYZ number. I guess we have to look at this. Which we want to do here. S15 fixed 16 number. S15 fixed 16 number. So what does that mean? Is a 4-byte signed... Is a fixed signed 4-byte 32-bit quantity which has 16 fractional bits, as shown in table 4. Oh, I see. So it's the sign bit followed by 15 bits followed by 16 bits. So negative has the sign bit set, then this. I understand. So this is, here we have const, what is this thing called? S15 fixed 16. And this is gonna have a U32 inside. Maybe we actually do like this. Sign followed by what is the A and B part of like A dot B? I can't remember what this is called. It's like fractional integer fractional maybe is a way to call this. And can we just parse this directly? I don't know how that works if you ask for like a big endian parse this thing. There's a good chance that we parse this wrong, but we'll see. We will see. So NCIA XYZ. This is wrong. Because this is a XYZ number, should have 3 of these things. So this should be an XYZ number here. Expected type this. Oh, oops. XYZ number is made up of these guys. So he said that we should see 0.964, which we're just like not seeing, right? Yeah, we're seeing something fucking crazy here. So, oh, wait, is this the wrong thing though? Oh, hold on, I want to go back to the sample profile. Yeah, I mean, this is clearly wrong. So can we look at this a little bit closer? So this is a big endian number. We might just need to parse this manually. So we want to do like a... and then maybe we can just actually do something more like this, where this guy can just become... I guess it's fine. I guess it's fine. So this is read take int as a U32 big endian encoded, right? Then we say return sign is truncate val shifted left by 31 30 31 30 31 surely. Integer is truncate val shift left by 16 or shift right I should say, and then we want to and 0x7f here, and then fractional is val and ff, something like that. I'm not sure about like order here, so I'm just gonna huck a couple brackets on here, and then I think that's right. So then when we parse an XYZ number, this guy probably doesn't have to be packed anymore. But he's going to return one of these based off of parsing from a reader. Bang, bang, boom. And what's he got? It's like return is just like triple parse, right? Like this. Cool. And then our XYZ number should be a parse here. Is that a little better? So we have 214, 1.0, and 0.45. The value when rounded to, I mean, I think they're just making shit up a little bit, right? I mean, that Y 1.0 is at least seeming a little bit sane, but the X and Z are not. Can we hex dump and less this thing and take a little peek at what we expect to see here? So this is bytes 68 to 79. So what is, this is 16 here, times 2 is 32, times 3 is 48, times 4 is 16 times 4. I'm stupid. So here, this is going to be byte 64 here. So 68 to 79 would be these 4, right? So we're expecting to see FD, F6, D6. This is 1.0, great, and 0.D3, 2D, right? So, F6, D6 is in decimal 63190. Is that what we see somewhere here? No. Oh, my mask is wrong. My mask is wrong. This is, oops. I was a little bit off here, right? 16-bit, I got confused because 2 letters I thought was 2 bytes, but it's not true. 2 letters is 2 nibbles. Does this look a little more right? Okay, 631540. And then does that match up with what we think it should be from reading it by hand? So calculator here for our F6D6 is 63190, which we see here. Great. And then what's our other one? It's D32D, which is base 10 54061, which we see here. Okay, so it's consistent with what we look at by hand, which is great, right? That's good. That proves something. That proves something. Actually, this doesn't have to be masked. This should be truncated. And I guess this can also just be truncated, actually, because it's a U15, so it already knows. Wait, that's hype. That's kind of sick. These, like, small integer types means that you don't have to do that, like, annoying masking. That's kind of cool. That's kind of cool. Okay, so what we got now? What's next on the list? Probably nothing that crazy. Okay, so then we have the tag table. So we've kind of got the header parsed to the amount that we care about, right? I guess we should probably put creator as a packed string at the very least. At the very least. Yeah, so this says we're created by Apple. Sure, fuck it. Okay. Reserve field is reserved. Okay, so then we should be at the tag table. The tag, which we guessed, right? We said when we look at this thing that there would be a bunch of sections. Oh, I guess that's what we guessed this was, though. Oh, no, we would have been this stuff. This is what we were guessing was the tag table, which is probably where we are. It acts as a table of contents for the tags and index into the tag data element in the profiles. It shall consist of a 4-byte entry that contains a count of the number of tags in the table, followed by a series of 12-byte entries with 1 entry for each tag. 4-byte entry contains a count of the number of tags in the table. And then each tag is 12 bytes. Got it. So, tag table. And I think we will follow the same strategy here. This guy's probably going to take an allocator. Or a better way to do this is probably actually to construct this guy from an iterator, I think. Or as an iterator, right? So I think that we're actually going to say next on here, and he's going to give us the entry. And here we're going to have, like, in here, num entries is going to be parsed up front, which he said was a 4-byte entry. So we're going to have an init here that takes a reader. And he's going to return a tag table iter. And he is going to hold the reader inside. I think that this is the way I want to do this. That way we can kind of do this without allocating. Okay, so every time we go next, we have an entry of we don't know what yet. Right? So we'll figure this out in a second. But this guy is like, I am a tag table iter. And in here, I'm going to, I guess we have to keep our count here. So he's going to say, I guess when we initialize this thing, sorry for going out of order. It's just how I think. So if you're like, why are we jumping around like this? There's no good reason. It's just like, I think very non-linearly. So if you're wondering, that's what's happening. This guy has to say, let's take a U32. Why are we jumping around? Don't know, brain broken. Yeah. There we go. Okay, so we get some entries, and we then are good to go. So we got like num entries is num entries. I think it's like actually like just the last thing I saw is the last thing I want to think about. Big endian is dumb. It's nice when I'm reading the hex dump. I kind of like the numbers being in order when I'm reading it. That's what I'm calling from now. Yes, dumb endian. Okay. What are we doing? Hello. We are working on generating color profiles to tell the GPU to adjust the colors on our monitor so that I can fucking see when I play video games. Why are you jumping around? My brain works in big endian. Yeah. Okay. So here we're gonna do like get me some 12 bytes, I guess. And then when I call take on a reader here, like what does that fucking do? He does a peek and toss, right? That makes sense. That makes sense. Okay. So now all we have to do is figure out what these entries are. So the tag following the tag count should consist of a 4-byte tag signature, 4-byte offset. So this sounds like a packed string based off what we saw on the hex dump and like everything else that we've seen that has signatures. 4-byte offset to define the beginning of a tag data element. So this is offset. And 4-byte identifying the length. Pipe. So here we need to say if I is less than the num entries, or I guess if he's greater than or equal to, we return null. We're done iterating. Then we can increase I, take the next fucking 12 bytes, try here because it might fail. If it fails, we fuck up. Are you using NVIDIA GPU? Nope. Normal people adjust the brightness for it. We need ICC from scratch and zig. Yeah. What more could you ask for? I'm playing Arc on PS5 on a Sunday day. I can't see the shit, so understandable. Yeah, I've been changing my monitor settings to make it not shit for now, but it's like so garbage, dude. It's so frustrating. All right. So this should be able to like once we've parsed the header, we should be able to be like, what do we call this thing? Tag iterator is tag table iterator init from reader. And that thing can fail because he does a read in his initialization. And then we go, while we get a new tag, let's print that shit. And I guess here we are doing a little format function, which takes self as an entry and a writer as a stood IO writer, and we're doing something like print, I guess it's like the signature offset len. No field name val. So true. So here we have, I think we can get away with this guy being a slice of U8. I think. Offs is going to be a, I guess we should do this actually. Take 4. No, it has to be like this actually. It doesn't. We need to take 12 to make sure that the signature memory stays valid, and then we do like offs is try stood mem maybe. How do I do this without a reader? Bytes as. How do I do this like with endian shit? There's bytes as value, but I kind of want something that like bytes as value with endianness on std_mem. What does the implementation of takeInt do here? Std_mem readInt, that's what I was looking for. Std_mem readInt. U32 val 4 to 8 as big, and then len is the same shit, but from 8 to 12. I'll start with this off topic. Can I ask about your journey of learning how to code? I coded a lot. I don't know. I started in high school, and liked it, so did it a lot. And then eventually ended up in school for it. However, I don't really think the school was really that important in terms of like ability. It is important in terms of like opening opportunities. But I went to like computer engineering school, and then I got a job, and then I kept coding off at my job and at night because I like coding. And then I quit my job, and now I code. It's about it. It's just like I like making stuff, so I make stuff. Why not a packed string? Because I don't think there's a need to copy here. We can just reference the memory in the reader buffer instead of copying it out. Was kind of my thought, because these tags I think are going to be short-lived. Like we're kind of saying like we expect this stuff to not be if you want to copy it, you can, was kind of what I was thinking. Maybe that's a bad decision, but that was the reasoning behind it. I think this guy needs a try, and then he's also mad about something else. Union type found U32. Oh, because I guess this can't technically fail. Interesting. No field format in U8, because now this is format as a string, not a thing. And there's our tag table, baby. That looks sane, right? So we see lengths that are relatively sanely sized. We see monotonically increasing offsets, which is good. And we see that the gaps in these things are changing by the order of magnitude of the thing on the right? So probably this is correct. Probably this is correct. So what's next? What is next? I guess now we have to like look at a tag that we care about. Why is it big endian there? Your format is big endian, or Nix is your hardware? Yeah, it's the format is big endian. So we're saying the data that we got is encoded as big endian, and if I'm big endian, then you can just like copy that shit. But if I'm little endian, which I am, you have to do the byte swap. And it's just like saying it that way instead of like byte swapping yourself. I think it just kind of makes sense, right? You say like read is big, read from a big thing. Okay. So now the question is if I want to fuck up my gamma, what do I do? And instead of looking at this sample profile, let's look at this sRGB thing and see what they did. So they have a targ thing that seems to have the majority of the data in here, right? Like, of all the things in here, targ seems to be the interesting one. However, they still do have all of these things, which I assume are like defining color spaces, maybe? Like target color space, RGB maybe, and like CIE color space maybe? I don't really know. Maybe we should look at these. Let's look at these headers and see if they tell us anything interesting. I think that is probably the play here. Okay, so I guess what are we? This sRGB profile, which we don't really know if is right. Can I apply this actually to my monitor? You guys won't see this, but if I see that it has an effect, then that would be nice for me. Which it does. You guys can't tell, but I can. So at the very least, this is encoded in a way that like works for what I'm asking it to do. Let's try to figure out what these things are. So the question is what type of profile are we, right? We're looking, I assume, let's see, let's look at the table contents again. Table contents. So we've got types that we don't care about. We have conformance. Maybe this is worth reading. Profile, connection space, rendering intents, and device encoding. We have required tags here at 8. And then profile requirements, it's chapter 7, which is what we just read. But maybe we should read the general requirements here. Oh, I think that was just the table at the start. And then we have tag definitions at chapter 9. And then more detailed information at chapter 10. Okay. Yeah, let's start with chapter 6. I think that sounds most interesting. Profile space, rendering intents, and device encoding. So this is at page 9, which is offset by a bunch. So this is, 15. So plus 15. So 9 plus 15 is 25, 24-ish. Okay. Profile connection space, rendering intents, and device encoding. The PCS is the reference color space. Okay, PCS. That's like some letters that we've seen. I don't know what they mean yet. In which colors are encoded in order to provide an interface for connecting source and destination transforms. So my understanding, based off like the slim reading that we did the other day, is that like you have like device space where like the things make sense for the device, and you convert that into this like common format that you can use to stitch these things together, right? Because like we said at the very beginning, you might have like a camera followed by a monitor followed by a printer. All of these guys want to work in a common space, so you don't have to do conversions from like camera to monitor space directly. The monitor can just kind of say like, I have common space to monitor, and the camera converts to common space and all that shit. 4 rendering intents are specified. So this is kind of what we saw. There was a difference between the sample profile that we got and the like gamma curve profile that we have. Each represents a type of color rendering that is useful for various imaging workflows. The colorimetric intents preserve colorimetry, no U by the way, of in-gamut colors, yes U by the way, at the expense of out-of-gamut colors. Where gamut is like, I don't know what gamut means. Yeah, you see like this picture, right? So I think gamut is like the stuff in the triangle in this big picture, where like this is the CIE color space, I think, with like XY, something like that. I don't know. I'm not a color guy. I just want to fucking see in a video game, okay? Don't ask me questions. The mapping of out-of-gamut colors is not specified, but should be consistent with the intent to use the transform. Perceptual and saturation rendering intents modify colorimetric values to account for any differences between devices. Sure. The requirements for these rendering intents are discussed in 6.2. Great. And then further in Annex D. Okay. Profiles are required to contain transforms for one or more of these rendering intents. Sure. Clause 6 specifies which rendering intents are required and which are optionals. Okay. Are clauses the same as chapters? What is a clause? I guess not, because this guy doesn't say clause. So clause is something else. Okay. The colorimetric rendering intents operate on a measurement-based colorimetric values as adapted to the PCS adopted white color chromaticity. Dude, my brain's just like, I don't know what any of these words mean. Blah, blah, blah. Chromatic adaptation tag. Okay. For the other intent transformations shall be assumed to be relative to the PCS limited. Okay. For all of these transformations, profiles are not required to specify any chromatic adaptation. Okay. I want to know what the intents are for. Media relative. Transformations for the media relative colorimetric intent shall rescale the in-gamut chromatically adapted tri-stimulus values. So this is probably like for my eyeballs. I think tri-stimulus is referring to like literally like the stimulating of my fucking 3 cones. Oh, is that what the CIE color space is? Is like how much do my cones fucking activate? That's kind of funny. Such that the white point of the actual medium is mapped to the PCS white point. You get 3 RGB. Are you red-green colorblind or something, so you only get 2? ICC absolute. Transformation shall leave the chromatically adapted tri-stimulus values of the in-gamut colors unchanged. Then what the fuck is the point? We've been over this? I think. Some of it. I seem to remember talking about tri-stimulus the other day when we were doing our like pre-reading. D to B3 and B to D3 tags contain separate transforms for the ICC absolute colorimetric intent. This allows for an absolute expression of colorimetric data. What? These do not contain a separate transform through the ICC absolute colorimetric. Were either of ours ICC absolute? One we had was perceptual, and one was media relative. So I guess we'll just ignore this one for now because I don't understand. Perceptual transforms. PCS values represent hypothetical measurements of color reproduction on the reference reflective medium. By extension, for the perceptual intent, the PCS represents the appearance of that reproduction as viewed in the reference viewing environment by human observer. I see. So we probably want media relative, right? If we're trying to like apply a gamma curve to our thing, we want to rescale these things. Maybe we want ICC absolute, but there's a lot of words in here. So I feel like, given that that guy who made these sRGB curves is using media relative, and based off the fact that I agree, I think that we will probably do that. So that is the profile we're looking at. So I guess we want to look at how this media relative thing works. So, media relative. Like, I guess we can guess that this guy has, like, the targ thing is important, right? Because that's what we see here and not in the other one, right? And maybe VCGT? No, VCGT is in both. Okay, so I want to see targ. What up with targ? What up with the targ tag? So that'll be in, like, chapter 9 or something? Tag listing. Tag definitions. So page 31 plus 15, it's like 45-ish. Here we go. Okay. The public tags currently defined by ICC are listed in 9.2 in alphabetical order. All tags, including private tags, have as their first 4 bytes a tag signature. Great. Each entry in 9.2 contains the tag signatures that shall be used for that tag, the permitted tag types for each tag, and a brief description of the purpose. Perfect. So, oh, I see. So we have profile class. So we want to be display, right? We want to be display. I assume, is that what this guy is? Monitor. Which, did we get a definition of what monitor means here? Display profile. Perfect. Perfect. So we want to be this guy. So A to B0 tag is device perceptual, colorimetric, saturation. Perceptual, colorimetric, saturation. Okay. None of these say targ. A to B and B to A represent a model that can include multidimensional lookup tables for, okay. Okay. Then none of this is like where the data is, right? Well, maybe, is this what like these guys are maybe? These like R, X, Y, Z, G, X, Y, Z, B, X, Y, Z? And then maybe these are just like linear mappings, so they're really short. That's like definitely an option in here. Okay. I want to find this targ thing. I want to understand what that means. Targ. Car target tag. This tag just contains the name of the registered characterization dataset, or it contains the measurement data for a characterization target. This tag is provided so that distributed utilities can identify the underlying characterization data and create transforms on the fly, or check the current performance against the original device performance. The first 7 characters of the text shall display. Interesting. If the first characters are ICCH det, then the remainder of the text shall be a single space followed by the reference name of the characterization data. If the first character match one of the identifiers listed in the NCIRSS standard, then the tag embeds the exact data file format in that standard. Whoa. So is this optional? Feels optional. I feel like this is like, hey, just so you know, I created this thing by using this data, but like, I don't think that like any ICC profiles are like reparsing this data. That seems crazy, right? Which makes me think that now I think that these guys are the more interesting guys. There's a required change factor. Yeah, I did see that. I did see that. So we are probably this one, right? Component matrix display. Right? So here we have description, right? We see description. We see copyright here, probably CPRT, media white point here. Then we have like RGB twice, which would be this stuff. What is BKPT? Maybe that's extra. Chromatic add, yeah, what is arts? Not in here. VCGT. VCGT. Not shown anywhere either, which is interesting. VCGT ICC. What is this thing? What does it mean? Graphics card lookup table from the video card graphics table, maybe, or something like that. Why don't I see that in this spec? VCGT, am I crazy? Yeah, interesting. Interesting. Okay, let's look and start by trying to figure out what is in these RGB sections. I think that's kind of the most interesting piece here. So can we maybe just kind of print let me think for a second. So you can't really navigate the reader while you're iterating the tags, which is kind of fucked. So we kind of have to say like I think read here is a better word. And also, this guy taking in the reader just kind of like flags a little more what is happening here, because it's like likely that we would fuck it up. You know what I mean? If we didn't do it. Like, I think that I'm likely to fuck this up. So kind of moving this like this makes it clear that this guy is reading more, like reading each tag. And then the question becomes is like, how do I want to say, I want to find this table and I want to go read it, right? You can store in here like offsets. So maybe we have like relevant tags. And in here we can just put like VCGT and like RXYZ or something, right? For now. And here we can do like stood meta string to enum of relevant tags from the tag sig, right? If we can do this, This is the relevant tag. We say offsets is going to be a stud enum array using relevant tags to usize, or u32 probably. Yeah, something like this. Are we allowed to do undefined? How does this thing work? Yeah, init default, maybe. Maybe like this. Video card gamma table. Ooh, found here. That seems interesting. That seems interesting. Someone from LLMs are saying VCGT tag is a non-standard component within an ICC that contains 1D lookup tables, just displays gamma and grayscale. That is basically exactly what I want, huh? Which would make sense. That would make sense. So it's possible that these guys are just kind of putting in like the base, like do nothing on all of the XYZ RGB things, and then throwing all the actual interesting parts in the gamma table. That seems likely based off what you guys have said there. Okay. And this is probably more like a segment info, offs, and len like this. And we will throw that in here. And I guess here we should probably write undefined, actually. Maybe, I'm not really sure. Okay. So now we have these things cached for the pieces that we care about, and then we can like advance the reader to those places and look at them, I think. Is the offset defined from the start or from the location of the tag? Surely from the start, right? Surely it's from the start. So for offsets, I guess we have like iterator, offs iter. While offs iterator next, we have entry, and in here we're looking at like entry key, and we say like stud debug print data for this guy. And then we dump it. So we go like, can we like hexdump? Maybe that's kind of like the way, right? We show like 16 bytes at a time. And maybe we do, I guess we like advance the reader to this place. So we do like reader seek to entry value offs like this. And then we go like, maybe kind of go like this, while I is less than entry len, maybe. This guy is a usize, probably. And then we go like for this, how do we hex dump? I guess we go like stud debug print like the value, so I here probably, and then this thing probably needs like a minimum length. How do you specify the length of this thing? Colon fill alignment width. So fill is a single byte which is used to pad format numbers. So 0 alignment is right aligned, and then width. So it's 0 arrow, and then let's say that we want this thing to be like 8 bytes wide or something. Const end here is I plus 16, but maybe we need to cap this, so it's like min of this and entry len here, and then defer I equals end for 0 to end for I to end, I guess. We look at we probably do like reader take take len, I guess is probably better. So there's going to be the minimum of 16 or entry len minus I. There we go. And then defer I plus equals take len. And we have take len here. And this is the data. And then for each byte in this thing, we have to print that thing. So we do a little 0 fill, 2 byte align, like make sure we're 2 width, 0 padded, whatever, with a space. I think that's right. Something like that. Expected type, this thing found type. Yeah, I don't know what the fuck I'm doing here. Init values. What the fuck am I supposed to do here? Init values. What is the point of having this init undefined? Let's just do that. Offsets RT expected U size found relevant tags. What? What? What is? Oh, I have to do get pointer. There we go. Error unit is ignored. And entry len is entry value len or something, probably. Data needs to be take tried to read out the data. And this guy's like, yo, you gotta put that shit in a struct. And it's like, okay, fine. Like, you can be like that. And then here, what is happening? Expected tuple or struct found U size. Where? Did I do that more than once? 222. Yep, I did do it more than once. Classic. We probably should do a new line at the end of each chunk of 16. And then we're getting close. That's actually not that bad. That's not bad at all. This guy needs a space here. And then the real hexdump interface looks kind of more like this, I think. Nice. And then we can actually put the character list on the right as well if we really want to get fucking crazy with it, right? I think it's actually just like this. Print. I think we have to do like if is ASCII on B, we print the character. Right, so kind of go like this, and then otherwise, like the hex dump thing to do is to put a dot, right? I think you write a dot there instead, and then here we need to fucking put the table thing here. Okay. We're close. Too few arguments somewhere. Yeah, true. Close. If is ASCII, print this. Oh, there's probably something better here, right? Because there's a bunch of stuff that is ASCII that is not printable. So is print is what we want here. Nice, dude. Nice. Look at that. We got like a fucking inline hexdump. That's not that bad. We did it. Okay. And so now the question is like, okay, what is in this RXYZ section? He's got like the header, XYZ. So this is good. We see some like proof that we are parsing this stuff correctly because the header shows up again, right? Then here we see 4 zeros. 1, 2, 3, right? So it seems like we have one XYZ value for this, which is interesting. I would have expected this to be some sort of mapping. But maybe this is more like a base color or something. I want to look at RTRC as well. What's in there? RTRC, so this is a curve, which is interesting. Oh, interesting. Yeah, so this is more like the type of the data, right? So this is like XYZ space. Here's a thing. Then this is a curve. And in this curve, it looks a little bit like we're seeing like monotonically increasing data, right? If you just look down like the left column here, we're seeing like numbers that go up, right? So if we assume that these are like big endian encoded numbers of some form, that would make sense, right? So maybe this is like a color curve for red. So can we look at that? Curve. Curve type encoding. The curve type contains a 4-byte count value and a one-dimensional table of 2-byte values. Okay, so we were close. So we see curve, we see reserved, then 8 to 11. So that's 1, 2, 3, 4, 1, 2, 3, 4. Oh, fuck. Okay. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So we see like, what is that? 2 to the power of 3? Is that 255 values? No. That's, yeah. 256 values of this thing. Followed by actual values. So these are all U16 numbers. U96. Am I stupid? This is 256, no? Field length bytes is 2 to the n. If n equals 1, the field length is 2 bytes. What? Oh, I see. Actual curve values starting with zeros. Okay, the curve type embodies a one-dimensional function which maps an input value in the domain of the function to an output value in the range of the function. Sure. The domain and range, so just x, y axis, are the domain and range values are in the range 0, 0 to 1, 0. So when n is 0, identity response is assumed. When n is equal to 1, the curve type will be interpreted as a value, as a gamma value encoded as a U8 fixed 8 number. When n is greater than 1, the curve values are defined as follows. The first entry represents the input 0, 0. The last entry represents the value 1, 0. And the intermediate entries are uniformly spaced in the increments shared between them. These entries are encoded as U16 numbers. Oh, sure. So 65535 is 1. When they say 0 to 1, they mean 0 to like int max. And values in between are obtained through linear interp. So I guess what makes sense for us to do here, if we're trying to figure out what this guy has done in his little sRGB gamma thing, is like, did he apply this here? Right? I want to come back to the VCGD thing as well. But like, if we were to do this way, does that work? Right? So if we parse this, we should be able to like piecewise graph this stuff and see what it looks like. And so all we have to do is spit out a CSV, I think. Yeah, so let's do this. Switch on entry key. And if we are... Wait, which one was the curve? RTRC, right? So if we are RTRC, we go back to the beginning. And we rip the first, I guess we assert that entry, like I guess we do like reader take for, this is the like, the content type or something. If this is not curve, then we have a problem. So we say a return error not curve. Then what was the other parts of this thing? Take for ditch 4 bytes. Then count the count. So this is a take int u32 for our big. Sorry, what am I saying? And we go like for 0 to count, we do reader interface take int, right? And this is a u16 fixed, which I think we don't really have to think about very much. And I think we just kind of rip this shit into a file somewhere. rtrc out. Create file, rtrc as a CSV. We don't give a fuck about create options, and we say like, we probably want like a rtrc out writer. Out writer rtrc out buff. Which is gonna be like this. We say, yo, print me this val followed by a comma. Maybe by a new line, actually. And then we flush this thing. Okay. Let's take a look at that and see if it makes sense. Count here. And print, he's like, yo, this thing's gotta be variable, so true. Okay, and then can we do like a LibreOffice angle at this? LibreOffice Calc, let's graph that shit. I guess we can like also just less it first to make sure it's like sane. Looks sane to me. Those are numbers that are going up in the range of 0 to U16 max. That is huge for us. And we can just take little peek skis. Once this thing finishes. I guess we could have gone a little crazy and like tried to make like an HTML canvas graph or something, which is like very doable, but that seems like we're going too far, right? We gotta draw the line somewhere. And we can just do this. We can just do this. Data, chart, insert, chart. I mean, so yeah, you can tell what this guy's done, right? So in the red channel of this thing, this gamma 0.55 is like an inverse gamma curve, right? And so probably if we look at the like gamma 1 point whatever, like this is gonna be the other way, right? So we run this again. And then we LibreOffice this thing again. And we should see like the inverse curve almost. Insert chart. They do look the fucking same, huh? Well, not exactly the same, actually. 1.5. Oh, hold on. I'm an idiot. You have to do more than copy the file. I'm an idiot. I'm an idiot. I'm an idiot. I'm an idiot. I don't need to hear it. You do have to fucking open the file that you copy. Still same shit though, actually. Oopsies. Chart. Which kind of explains why these two things looked fucking identical in when we opened them with MPV, right? So maybe they're not like identical, but maybe the gammas are. Can we do gamma like 1.0? Like this. What is going on here? What does like 1 look like? Because I would think that gamma 1 would look like a straight line. That would be my assumption here. But who knows? Yeah, I mean, they all look like they have kind of this shit happening. So that also makes sense why when we ran MPV earlier. Do I have MPV open somewhere? Let me look. Like they didn't have inverse effects from each other, at least, right? So like 1.0G ICC looks dark as fuck compared to like the original. I mean, it's not like the original also is dark as fuck, but like that 1.0G ICC profile made it like pitch black, right? So like whatever's happening there means that like these aren't what I thought they were, is the answer. That's the answer. Or he's injecting the data in the VGCT section or something. Okay, so what I think I would like to try next is maybe just shoving some linear curves in there and seeing what happens, right? So what are we expecting in here? We have like how close are we to understanding this profile, or what is necessary here, right? In the section where they were talking about the required sections, required. What was it called? It was in the table of contents. It was called profile requirements. Was that what it was? Required tags at 8. So we think that we are a display profile. This was not where it was, but this is. Yeah, there was something else. Blue TRC. I'm confused a little bit. I'm a little confused about where we saw the section where it's like, you need this. Oh, here. This is in Appendix G. We just happened to end up here by mistake. That's funny. Yeah, so we want this 3-component based display profile and required tags. So we understand somewhat these tone reproduction curve sections. We do not understand any of the other sections yet, right? So I guess that's probably the next thing to play with, is trying to find out what this blue matrix column, the third column in the matrix used in the transforms, in the matrix TRC transforms. So should these just be like ones? The first, right? So I imagine that this is a matrix that is global, used for everybody, that you say, take this thing, map it to with this, and then apply this matrix to it after? This column is combined. Yeah, it doesn't. I don't know if it's before or after is the thing. So that makes sense why we're seeing 3 numbers in these. So these 9 numbers together make up some sort of color matrix, which you could probably use to do like color rotation and stuff, which is kind of fun. Okay, yeah, what we need to do is create a tag. The next goal, I think, is to create an ICC profile that does nothing, and then prove that we can like really fuck shit up with it. But we are at 2 hours almost exactly. We're 1:55. So I think that this is kind of like a natural place to kind of call it and say we'll come back tomorrow. So what have we done today? We've kind of got through kind of the bones of an ICC profile, right? So we have the top level header parsed. We're not really using a lot of this stuff right now, but we have the information available to us if we need it. We have iterated through some of the sections of this thing, and we have a bit of an idea about where the color curves are defined. We know that there's this matrix thing, but we don't know what it does yet. And I think we figure that out tomorrow. This copyright tag, I think, is easy to fix later. Media white point tag, we can probably just copy from somewhere. This, I'm not 100% sure. The chromatic aberration tag, probably this is like what color white is, so you just say this is white as well, probably. And I think we're almost there, right? Assuming, we don't know what that VCGT thing is yet either, but I'm assuming that we don't need it considering it's optional, right? So maybe it's like an optimization, but maybe one that we don't need. Cool. So I hope that was fun and interesting for you guys. We have parsed we've done a shitty parser of some file format that we don't understand. That's what we did today. And tomorrow we will make a shitty serializer for that format that we don't understand. But hopefully we get somewhere interesting. So thanks for watching. If you like what you saw, we stream most days from 12:30 to 4 Pacific time. However, during Christmas break, we have not been faithful to that schedule. So we have been kind of doing more of a sporadic 12:30 to 2 ish, or 12:30 to 3. But we will hopefully get back on schedule after New Year's. We should be back tomorrow to do the second part of this, but I won't make any promises because, you know, it's just so hard when all my friends are on Christmas break and they're playing games like, I want in. I want to get in on the fucking Dota, man. I got to get in. But anyways, we'll see. Thanks for watching. YouTube, peace out, and Twitch, let's find someone to raid.